Following clip you will see in time lapse, so it will appear choppy, so I apologize for that. What you're looking at here right now is a flat pancake coil of plastic fiber optic cable. It's wrapped in a spiral pattern with 28 turns. What I will do in this experiment is shine a green laser pointer into the end there of the fibers so that the light goes around the spiral, goes around the coil. In an older video, I called this an optical warp coil, and my thinking was that running the photons around in a coil would concentrate a type of space-time metric modification. Now I know that when I use that sort of terminology, it may cause some of you to balk because you'll immediately say, well, you can't do anything like that with such small energy levels. And if I say something like warping the space-time metric, then it ties it into the Einstein paradigm and makes it immediately dismissible. However, in this clip and in the following experiments, I take what I did earlier and I try some different approaches. And also let me apologize for the long delay in releasing this. One of those changes or differences being is that the coil you can see there has a layer of aluminum tape on it. Because aluminum tape is reflective, I wanted to see if I could contain the light and concentrate it more and thereby enhance the effect. The other thing I tried was putting the whole assembly, including the analytical balance, underneath a big a transparent draft shield which I built. Here's the same steel puck I used before and I will use again. I'll place the steel puck with the coil on top of it, on top of this wooden beam here. One end will rest upon this scissor stand here. And here's the whole setup underneath the draft shield. So here you'll see a graph of the results here over time. The blue square wave lines indicate the time when the laser is on. As you can see in the background there, the green light. And then the red indicates the trend in weight readings. So looking at the trend there, we can see that there isn't really much of a correlation between when the light's on and when it's off in terms of the weight changes. However, if you stick around towards later in this video, I'll show another setup where there is indeed pretty clear correlation between when the light's on and changes in weight. And there is a certain reason for that. Now I admit one of the challenges with this particular test I'm doing here is holding my hand steady enough to make sure the light laser beam actually gets in the end of the fiber optic cable, and that's difficult to do. And that's one of the reasons why I hated this particular experiment. But for the sake of consistency, I did it this way, and I will do it this way again in later clips here in this video. In case it wasn't clear before, the yellow arrows there are just pointing to the time frame there when the laser beam is on. Also shown by the blue square waves there. What might be easy to completely overlook, though, is in fact that there is some change going on here, already to the effect of about 22 milligrams, which is a huge amount of variation for this particular analytical balance, and is a subject of continued research on my part. There is other scientific literature coming out of the Russian side, which talks about these kinds of effects and strange forces acting on isolated asymmetric pendulums and that sort of thing, where these forces even appear when the test objects are completely isolated thermally from the surroundings and that sort of thing. And in this case here, the test mass is within a box, which would eliminate most currents of air. Temperature would be relatively stable through the whole test here. And the setup is on concrete. Regarding the work of the Russian scientists, I may go deeper into that in a later video, as I am still researching it. But let us move on to the next part. So I'm doing some more work with this. I have rewound this type of pancake coil out of the same plastic fiber. And it's just placed on top of this. This is a bismuth, just a bismuth disc. And sitting on here on this balance, let me just tear this out here. So, one sec here. Just to give some idea what sort of weight or sort of force would be measured downward here on the plate. About 48 grams. And with the coil on top there, about 48.7. So what's different about this arrangement here is this piece of wood here is a lot thicker, for one. So it's not going to flex or change its form. I think it would be negligible, right? So, and other than that, I've tried to keep pretty much everything the same as before. So in this experiment, I'm positioned about 2 or 3 feet away from the setup. And I've also been recording the data over about 40 minutes in the one case where I'm shining the laser through the coil. So about 40 minutes where I have it for about 5 minutes where I do nothing and I just let it settle. And then for the next 5 minutes, I try to shine laser light into here, but it's very difficult because it's a very small target, right? So, but I try. So I do that for about 5 minutes and then I turn it off and let it go back to its original baseline. And I do that back and forth for about 40 minutes. And another thing I do here is I turn the lights off. Because since this experiment is sensitive to light, I want to make sure I have a dark background. You'll see me following the same procedure. So here's the results from the experiment where I am shining the green laser into the pancake coil. So here is, this represents just over 45 minutes. And here this represents the reading on the balance, which is actually negative. So as this goes up, what that means is it's going more negative, meaning more of a weight loss. So the first 5 minutes here, this is just what it does initially as it stabilizes. And then here from 5 to 10 is approximately where I'm shining the laser light into the coil. So there's a further reduction here in weight, so it goes negative a little more to from like 0.025 to 0.036, and that represents about 10. It's about 10 milligrams. And then from 10 to 15, approximately, the laser is off, and you can see the going back up towards 0, which would represent a slight increase in weight. And it sort of settles here, and then I turn the laser on again from like 15 to 20. So, and then off 20 to 25, 25 to 30. So it looks like there's a bit of a correlation in this case with the laser being on versus off. And then here, 35 to 40 would be on, and 40 to 45 would be off. So having done actually many different experiments with this now, and seeing results and not seeing results, I think what it is when the light goes through this, and this is not a perfect, it's actually a very poor conduit for light because the light leaks out everywhere. So I think it's the light, when it leaks out, it makes contact with the surface, the metal surface. In this case, bismuth, which is very dense. In the previous case, it was a piece of steel and a piece of copper, which are all fairly dense metals. So we have a dense mass that this rests upon. So the light spills out the sides. It's mostly contained going around the circle, so there's more light energy in the vicinity of the metal, just above its surface, which is an increased energy density, local energy density, which may, to a small extent, alter the refractive index of the space in the immediate vicinity of this plastic fiber, which I believe might have some influence on the gravitational weight or force of this metal. And so the next experiment I did here, with the same thing, I didn't change anything. Like, I left this on the beam here in the same position. I didn't touch it, didn't change anything. So all I'm doing, or all I did, was basically shine a green and a red laser on top, like this. And then the green one on top. I didn't attempt to try to get the laser light to coil around or go into the fiber, but merely just shine it on top. And so this is the result here. So this chart represents, this is about 15 minutes in total. So about every 2 minutes, in the beginning here is just nothing. It's just off, it's black, it's dark, no light. And it's 2 minutes here. I shine the lights on, the lasers. I shine the lasers on it. Lasers off, lasers on, lasers off, lasers on, lasers off. So I'm getting a delta W here of about, this is 0.042, this is 0.032. So about 10 milligrams. Weight loss, gain, loss, gain, loss, gain. And again, this, just the way this chart works, these are actually negative numbers. And here's the actual data. You can see these are negative. This is coming in from the scale every minute. So this is actually very consistent, I'd say, because this is 2 milligrams here each space. So 2, 4, 6, 8, 9. 1, 3, 5, 7, 9, 10. So the delta W, the delta weight, is fairly consistent in the 10 milligram ballpark. What I was really trying to do here is just replicate my previous results, because I figured if I can do that, then I can understand what's different and what's the same. And by seeing results and not seeing results, getting positive and negative results, I can determine what the difference was that gave me the results. So it appears that I want to have a leaky coil or leaky fiber. So the cheap plastic one is better. So I know I just did another video where I had the large coil of the glass fiber optic cable. This is the same kind of cable here. This is glass fiber, just without the outside insulation, which is quite thick. Now this actually winds quite easily compared to the plastic. The plastic is much springier, so this is much nicer to wind. However, I didn't get any results with this, even though you'd think that because the glass fiber is so much better for conducting the light, which it does very well. However, it's all contained inside the fiber pretty much, and then inside this plastic insulation here, and then inside this aluminum tape. So the light is not being allowed to fill a larger volume of space around the mass. So that's why I think this doesn't work, because it's not allowed to radiate outwards, to expand outwards. In this case here, you see this plastic is so much better at leaking light everywhere, all over the surface. So my conclusion is that the coil is really not needed. So here is another experiment I'm going to do very soon. These are all line lasers of different wavelengths. So what I'm going to do is shine these over top, kind of like how I did this experiment. I'm going to shine these beams over top, and then I'm going to look at how each wavelength has an effect, or what if the combination of these various wavelengths have a more pronounced effect. We'll see. And they are infrared to blue, which corresponds to like 1,000 nanometers or so to 450 nanometers, which is like a deep blue light. So in conclusion, it appears that windings are irrelevant, and this doesn't seem to work like an electromagnetic coil would, or a solenoid would, concentrating magnetic flux or energy. Also confining the light to a small space, like within the aluminum tape and the insulation of the glass fiber, seems to nullify any effect. What does seem to work, though, is when the light can radiate outwards through the plastic fiber and out into the space around, or even just the light beams shining upon or over top or underneath. And this also corresponds with the findings of Louis Rancourt and other researchers who have confirmed similar results. I hope this helps, and thanks for your support, and thanks for watching. And more to come.